Today we're going to go through exponential and logarithmic functions. So this lesson will mostly cover exponential functions, and then the logarithmic part will be in regards to solving exponential equations. And we'll go through a couple of examples of that. So I do want to start with a couple of notes, kind of the main areas of focus for exponential functions. And we're going to start with the general form of a transformed exponential equation. So y is equal to a times b raised to the x minus h plus k. I'll do k in green. Actually, instead of y, let's call this f of x. So f of x. If I have this function here, and I have what we're going to call a parent function, g of x, and let's define g of x as b to the x, then we say f of x is g of x transformed. How is it transformed? Well, we're going to start with the stretch slash compression factor. That's the a value. So if we multiply g of x by the number 2, that exponential function would be vertically stretched by a factor of 2. So we call that a stretch factor. If a is between 0 and 1, it's called a compression factor, and it would be compressed vertically by a factor of, it depends on what the number is, but if it was 1/2, it'd be compressed vertically by a factor of 2. Secondly, the k value on the outside indicates the vertical shift of our function. So the k value moves the function up and down. If k is positive, it moves it up. If k is negative, it moves it down. The horizontal shift is denoted by, the letter h, and so that will indicate whether or not the function is moving to the left or to the right. And then lastly, with exponential functions, the b value is going to come into play here. We say that the function has a reflection over the y-axis if b is a fraction. So like this. If I had g of x over here to the right, and instead of having b as the base of the exponent, I had 1 over b, then that would be a reflection over the y-axis. Another way you can write this, so let's say this can be written as b to the negative 1. So if the base of the exponent is a fraction, or if the exponent has a change in sign, that is a reflection over the y-axis. And what that will do is it'll transform the function from a growth factor, or from a exponential growth function to an exponential decay function, or vice versa. Okay? These are the most important notes of the unit, the transformations of exponential functions. Another couple of concepts I want to cover before we get started are these formulas here. So you should definitely have these formulas written in your notes and recognize when and how to use each one of these. Okay, so we're going to start with a problem set involving algebraic problems. Okay, so for problem set 1, number 1, we have a function, g of x, and g of x is defined as 4 to the x. And what we want to do is recognize the transformations that the function has undergone as we change the function itself. So for example, for number 1, what happens when we switch the sign on the outside? So that compression factor. So the number on the outside will determine how much the function is stretched vertically or compressed vertically. But remember, if we switch the sign in the front, it's a reflection over the x-axis. And so that's what we have here. This is a reflection over the x-axis. The x-axis. For letter B, it's basically the same thing as letter A, so let's write reflection over the x-axis. But there's another transformation, and that is a vertical shift 2 units up. So it's shifted 2 units up. Okay, letters C and D are also pretty similar. This gets into what we talked about with that B value. Another way you could write this is 1 over 4 to the x, which is the same thing as 1/4 raised to the x. And what this will do is it'll transform 4 to the x, which is an exponential growth function, into an exponential decay function. And what that looks like graphically is it's a reflection over the y-axis. Okay, so then for letter D, this is the reflection over the y-axis. And it's also shifted 1 unit down. Okay. So letter E is going to be a horizontal translation. So this is shifted 2 units. 2 units. Not left, but right. And this is shifted 3 units up. Okay. So those are transformations with exponential functions. Now, to wrap up problem set 1, let's solve a couple of exponential equations. So to get an exact answer here, you will need a calculator. But if we don't have a calculator, we can leave our answer in terms of the logarithm. In this case, it's going to be in terms of the natural logarithm. So we're going to be using logarithms to solve exponential equations. And so that's what I want you guys to focus on for the final, is not so much the properties of logarithms, but how we use logarithms to solve exponential equations. That's the most important part of logarithms for this class. So here we have a exponential equation. It is an exponential equation because the variable x is inside the exponent of the function. Okay. If we want to solve an exponential equation, the first thing we're going to do is isolate the exponential term. That's this right here. So to do that, we're going to divide by 2 on both sides. Remember, to undo an exponentiation, we have to take the logarithm of both sides. The base of the logarithm has to match the base of the exponent. And so in this case, the base of our logarithm needs to be e, or Euler's number, which is about 2.718. Like this. But instead of using log base e, we have a special name for this logarithm, and this is called the natural log. So we're going to write it like this. The natural log of e to the x minus 1 is equal to the natural log of 6. Okay. Because the base of the natural log is Euler's number, and the base of the exponent is also Euler's number, these functions will cancel each other out. And we're left with x minus 1 on the left-hand side. So the solution to this equation is the natural log of 6 plus 1. To get an actual numerical value, you'd have to plug this in your calculator, and this is approximately equal to 2.792. Okay, let's do the same thing with letter B over here. So this is 3e to the x plus 4 plus 2 equals 20. Okay. So we're going to isolate this term right here. The first thing we should do is subtract 2 on both sides. After that, let's divide by 3. Now we're going to take the natural log of both sides. And just recognize the base of the natural log is Euler's number, so the reason why we're taking the natural log of both sides is because the base of our exponent is Euler's number, e. Had the base of our exponent been like 7, we would take log base 7. This is x plus 4 is equal to the natural log of 6. So x is equal to the natural log of 6 minus 4. Okay, and that's the solution to the second equation here. And this is approximately equal to, if you plug this in your calculator, about negative 2.208. Okay. So let's wrap up this video by going through graphical problems associated with exponential functions. In problem set 2, we're going to go through 2 questions involving kind of analyzing the graphs of exponential functions and then answering some questions associated with the graphs of exponential functions. So for the first question, we are given an exponential function, and what we want to do is determine what the equation for this graph is. So here is the general form that we've been using. And if you guys remember this back from Unit 6, we kept this simple by assuming there was no horizontal shift. And so we're going to kind of keep with that. And for this question, we're going to assume that there's no horizontal shift, meaning that the h value would be 0. The first thing we want to do is determine the horizontal asymptote. The horizontal asymptote is the value, the y value, where the function levels off. And in this case, that's going to be y equals negative 2. The horizontal asymptote is useful in this case because it will give us the k value. So the k value is equal to negative 2. Okay, next we're going to plug in the y-intercept. So the y-intercept in this case is located right here, and that's 0, 0. The y-intercept is useful because it will allow us to find the a value. And so the way we're going to use the y-intercept to find the a value is by plugging the y-intercept into our original equation. So if we know the horizontal asymptote, we can replace the plus k with a minus 2. And now we're going to replace the x with 0 and the y with 0 as well. Well, b to the 0, b is a number. Any number raised to the 0 is equal to 1. So that just becomes 1. And so 0 is equal to a times 1, which is just a minus 2. And so the a value in this case is equal to 2. Okay, and then lastly, we're going to find the b value. And then once we have the b value, we have everything we need to make the equation of this graph. So y is equal to 2, b to the x minus 2. And to find the b value, we're going to pick a point. So we're going to pick any point that's not the y-intercept. So there's a bunch of different points we could pick, but let's pick a point that has an integer. Because if the point has an integer, it'll be easier to work with algebraically. This is 1, 4. And so 4 is equal to 2. Actually, let me write it. I'll write it up here. 4 is equal to 2 times b raised to the first power minus 2. This is just 4 is equal to 2b minus 2, because b to the first is just b. So this is 6, if we add 2 on both sides, is equal to 2b, and therefore the b value is equal to 3. And so our solution, f of x, is equal to our a value, 2, times our b value, 3, raised to the x power, minus 2. And this is our answer. Okay, let's wrap this up by going through kind of a question where we're going to look at a graph of an exponential function as well as another exponential function that's not graphed, and then determine some key characteristics of that function. So here we have f of x, which is graphed here. And we have another function that is not graphed, but let's graph it real quick. So here's f of x. Let's call f. And there's g of x as well. So g of x, we don't know exactly what the function is, but we know that it has intercepts at 0, 6. So that's right here. -6, 0, 1, 0. And then we also know it has a maximum value at -2, 10, which is, it's going to be off the graph, but it's like right here. Has a maximum value there. So based on kind of the behavior or the location of these points, I think it's safe to assume that this is a quadratic function that looks kind of like this. So this is -6, 0, -2, 10, 0, 6, and this is 1, 0. And this point right here is 2, 0. Okay. So let's determine where each function is positive. So let's start here with a. Well, f of x is going to be positive on. And one important thing I want to point out is when you see this word where, that is an indication that we're going to be identifying x values. So the answer here is going to be an interval, but the interval is going to represent x values. So f is positive when it is above the x-axis. So we want to think, what are the x values where f is above the x-axis? Well, it's above the x-axis here. And the way we're going to represent the x values there is on the interval -∞ to 2, because that's the x value here where it stops going above the x-axis. Okay. Now let's determine where g is positive. So g is going to be positive when g is above the x-axis. And in this case, that is from here to here. So from the x value of the first x-intercept to the x value of the second x-intercept. And in this case, that is on the interval -6 to 1. Okay, and then let's wrap up this video by determining where each function is decreasing. So that's where it's going down from left to right. So notice how f of x starts up here and then it just levels down this way. As we go to the left, it will level off. However, the slope will always be negative. And so f of x is always decreasing. And so the way we write this is we say it's decreasing on the interval negative infinity to infinity. And that's it. You could also say all real numbers. I would also accept if you were always decreasing. I think that's fine as well. Okay. And g of x is going to be decreasing when it's going down from left to right. So we're going to start here, and then it's going to go down from left to right here. And so g of x is decreasing on the interval. It's going to be the x value of the maximum point, which is 2, negative 2. And then if we're going to the right forever, it's positive infinity. Not negative infinity, because it's not up and down, it's left to right. So it's going to be from negative 2 to infinity. Okay, that is it for this video. When you are finished with this video, let's transition to the additional practice here at 9.03c on the OneNote.